Morning again, and let's just dive into directly into the application of the machine learning for, namely the linear unmixing methods for the image analysis. So during the first lecture in this summer school, I have illustrated that we can use machine learning on all the stages of the microscopy operation. We can use it to analyze the data after it has been acquired. We can use machine learning during the data acquisition, sort of to transfer the data into the useful information in real time. And we can even analyze the data in real time and enact some form of the feedback to the microscope operation when the machine learning agent basically becomes your co-pilot in running the microscope. However, in order to use machine learning methods in this fashion, we need to first figure out what type of the knowledge we can extract out of the machine learning applied for images. And today we are going to go through the simplest form of the machine learning analysis of images, which is the application of the linear unmixing methods. So the same type of methods that I have illustrated a week ago for spectra. So the questions that we are going to answer is, first of all, why would we want to analyze images and image stacks? So why do we even need machine learning for that? Why is the human eye is not enough? Then I will illustrate the example of the workflow. So workflow is a magic word. Basically, it defines the sequence of actions that you take in order to accomplish something. The reason why we need this word is, first of all, it allows us to do things reproducibly and explainably. And secondly, development of new machine learning methods for image analysis very often becomes the problem of the defining the workflows for image analysis. And then we will discuss an exceptionally important issue of how do we build the descriptors. So it turns out that if we want to analyze the images, we need to figure out what are our building blocks in this analysis. So in the classical machine learning field, it is called feature engineering. So building the descriptors is essentially designing the features that will be that you choose in such a way as to answer the physics question that you have in mind. And then I'm going to illustrate few applications of the pipelines based on the simple principal component analysis for atomic and mesoscale images, and a few pipelines based on the k-means clustering. And then I will illustrate a few examples of how we can expand it using the other form of unmixing, such as Bayesian linear unmixing, independent component analysis, and how can we extend it to the video data and 4D STEM. So in all those cases, we effectively deal with the machine learning analysis of images. So let's start with a little bit of motivation. So one of the greatest thing about the electron microscopy is that you get to see absolutely fantastic images, which are really beautiful, which tell you something about the structure and very often about the properties of material. And the question becomes, can we somehow capture this complexity and interpret it and spread it into the elements that human can understand? So for example, if you look at this image, this is a complex oxide formed by molybdenum, vanadium, and tantalum, which was synthesized as the catalyst. And even by eye, you can clearly see that there are two phases here. So you have one phase which shows this beautiful tunnel structure. So presumably it is responsible for catalytic properties. You have another phase that looks perfectly hexagonal. If you look very carefully, you can see that this phase has a small number of the defects inside it. So maybe there is some additional defect structures. And then if you look even more carefully, you can argue that the interface between this phase and this phase has some form of intermediate structure. So maybe this is just a grain boundary, maybe this is, interface boundary, maybe this is amorphous phase, we don't know. So the natural question here becomes, can machine learning actually help us figure out what is the nature of the building blocks in this phase and this phase? and what are the atomic configuration of these building blocks. So if this were a single crystal, we, with the ideal translational periodicity, we of course would use the Fourier methods. But in this case, I'll show you that it really doesn't work all that well. So this is another example of the video. So this is the graphene with some contaminants, and the bright dots here are the silicon atoms. Again, as you can see, the graphene is not stationary in the electron microscope. It actually undergoes the beam damage. So you see how the defects forms, and the whole thing slowly forms apart. But again, the question is, can we identify the individual defects and building blocks inside this graphene which undergoes this transformation? So you can say that in this case, human eye can be a pretty good guide, for we can clearly differentiate this phase and this phase. In graphene's case, it would be a little bit different, but let's look at the more complex example. So these are two images of the nominally single crystal system. So this one, this is actually not electron microscopy. This is scanning tunneling microscopy, but it illustrates the principle of the looking at the image and see that there are clearly some details here. So if you look at this image carefully, you can see that there is sort of difference between the intensity of the individual spots. So here, for example, you can clearly see this dimers, and clear you can see that there is no dimers. So it looks like there is a mixture of two phases, but you really need to go pretty far off of the limb in order to be able to say that I clearly can see the difference by my eye. This is another example. So this is electron microscopy. And if you look at this image as a whole, you can sort of think that this is just a single crystal. Turns out this is absolutely not a single crystal. In fact, what we have here is that there is a substrate. This material is the ferroelectric material, and there are ferroelectric domain inside it. So the question becomes, how are we going to identify those structures? During his lecture, Gerd have shown you one example of doing that, when you determine the position of each atom, and then you calculate the value of the physical order parameter, for example, strain or the polarization. But in order to do that, you need to know in advance what is the order parameter inside this system. So imagine that you don't know the order parameter. So how do you discover the unknown? And that's exactly where machine learning can actually help us to do that. So can we use the Fourier transform? So Fourier transform is the very powerful method, obviously. And when you have a fundamentally new image, you always start with the FFT and look how it looks like. The problem, however, is that FFT is great to show you the details on the atomic level, but it is very susceptible to phenomena such as drift, extended defects, multiple grains. Essentially, if you have a image with a large number of the constitutive elements, the Fourier transform of the whole would be essentially a linear superposition of the Fourier transforms of the part. So essentially, we average out all interesting phenomena, except for the small, spatially uniform structural distortions. And it turns out that one way to solve this problem is to split the image into the image patches, so what we call a sliding window approach, and then try to run the Fourier transform on these images. So let's see how it works. So let's go back for our idea of the general linear unmixing. So you have seen the example of how it works for the spectral data. Turns out that it can work exactly the same way for the image data. So imagine that we start with our image. We split it into the image patches. So each image patch has a center. So you can think about it like we drag this window across the image and generate patches one by one. So if our image patches are of the pixel size n and our image is m, then we can build it, divide it roughly into m divided by n non-overlapping patches. Of course, we can take the more dense grid, then the patches will partially overlap. And this makes for better images, but you need to realize that the information in the overlapping patches is no longer independent. And then once we represent this image as the collection of patches, then we run exactly the linear unmixing analysis. So we represent our stack of patches as the linear combination of some loading matrix times the components. So our loading matrix will would represent how the patches vary across the whole image plane, and our components would basically be small images, which represent supposedly the elementary mechanism inside the system. Now, the question becomes, is there a right way to select these patches? So sampling over the rectangular grid is the most simple and in some sense most natural way of dividing the image data. In fact, exactly the same approach is being used by the convolutional neural networks. So when we get to this part and discuss the structure of the convolutional neural networks, how they take the information and start to down convert it into the latent variables through this funnel of filters, it's kind of almost the same. But the important thing is that if we divide the image into patches, we superimpose the continuous translational symmetry. This is probably the best we can do for the images which are not atomic resolution. But in some sense, from the informational theoretical point of view, this type of sampling represents the lack of the prior knowledge about the system. So if I don't know anything about my object, and I want to sample it effectively, I will sample it on the uniform grid. So if I don't know anything about what makes this image interesting, I'm going to sample it through the patches. You can say, okay, but atomically resolved images always have some form of the discrete translational symmetry. So there are special selected directions. Can we choose the patches following these directions? And the answer is theoretically yes. But practically, you don't know what these directions are. So unless this information is to provide to you before the image analysis, which in real world it never is, you cannot do that. So if you discover the symmetry, then you can create the patches following the symmetry. And this goes me to the second type of the descriptors we can select, which are the descriptor based on the determined atomic positions. So if we use the same approach that Gerd have shown on the previous lecture, we can find the position of all the atoms in the system, and then we can analyze the system structure one atom at a time. So one way to do that is to take the image, find the atomic positions, and then analyze the atomic positions only. So in some sense, we forget everything else there is there. We focus our attention only on the atomic positions within the image. So I'll show you the example of how it works. The problem with this approach will be that microscopy images, whether it's electron microscopy or scanning probe microscopy or what's not, they contain a lot of information that cannot be reduced to just atomic shape. For example, they have rich information in the shape of the atomic columns. If you have the atomic column that goes zigzag in the distortion in the beam direction, this column will look like an ellipse. Very often we have the sort of shadow information because of the interstitials, distortions, and so on in the system. So if we want to combine this type and this type descriptor together, we can create the patches centered on the individual atomic units. For example, if I want to analyze the properties of the silicon and graphene, what I can do is to find all the silicon atoms, create the patches centered on the silicon atom, but having a part of the graphene lattice around it. And then I can analyze the local chemical structures of these images. The interesting thing here, which was actually a very big showstopper that took us about a year to sort out, is that the microscopy image come with very interesting properties. They very often, you really don't know what orientation the individual unit will have in the image plane. It turns out that the biggest limitation for the linear analysis methods is if you have the same structural units, but which have a different rotations in the image plane. So in this case, we cannot use linear methods. We have to use the rotationally invariant autoencoders, and that's something that we are going to go through in 10 lectures from now. But for the time being, let's start with just the patches centered of atom. And then it turns out that we can do even more interesting things. So very often we deal with the image data, which is taken as a function of time, or in other words, videos. And very often these videos are detailed enough that we can trace the evolution of the object from one image frame to another image frame. This is not always possible. For example, if I look at the evolution of the graphene in the electron microscope, most of the time I cannot differentiate two different carbon atoms. So most of the time I cannot say that this is particularly this atom that jumped into that position. However, in some cases, I can actually trace the evolution of the domain wall, transformation fronts, and so on and so forth. And then I can introduce the descriptors when I choose my anchor point at one moment of time, but I determine the patch centered at the anchor point at the different moment of time. If I do that, then my definition of patches includes the time derivative of the property that I'm interested in. So in all cases, you create the descriptor that matches the physics of the problem that you're interested in. But this physics-based feature engineering is how you set your problem for the machine learning. So in this case, I want to analyze the image that I don't know anything about. In this case, I'm interested only in the atomic positions and bond distances and bond angles, but I don't care about anything else. In this case, I want to explore something related to specific type of features, so for example, chemical neighborhood. In this case, I want to explore the time dynamics. I'm pretty sure that there are multiple other ways to define the features. For example, nobody stops you from taking the image and somehow study the properties of some non-continuous neighborhood around it. It's just that we haven't encountered this type of problem before. Or maybe we didn't have imagination to set the problem like that. So next step is we have the patches. What do we do next? And the next thing is that we set up an analysis pipeline. So analysis pipeline is basically represent the sequence of operations that we do with our data. For example, this is how we can start with the image or video data. We create our descriptors. So descriptors is a patch, and each patch comes with a coordinate where it came from the image and the number of the frame if it is a video. We do something with the patches, so we can leave it as it is. This is the identity transform. We can use the Radon transform. So Radon transform is how you can identify the preferential directions within the patch. You can do the Fourier transform. So Gerd showed how it is used. You can define any other transform. For example, you can calculate a histogram. Whatever you feel will tell you something useful about the data. And then you have the same number of patches, and then you send it to some form of the dimensionality reduction method. So you can send it to the PCA, you can use the NMF, you can use Gaussian mixture model. So in this case, your dimensionality of the patch stack becomes much smaller. So you separate it in the components and the loading maps. And then you visualize what you got. You can visualize the descriptive statistics, you can visualize the loading maps, you can examine the components. So let's say 5 years ago, if you do something like this, you can publish a paper about it. By now, this is a relatively short program in the scikit-learn, so you just use it as the regular tool. But the idea of defining the pipeline is that your analysis become traceable, repeatable, explainable to the extent possible, and transferable. And another very important reason why we introduce the pipeline as the component is because it allows you to tune the hyperparameters and optimize the pipelines. So what I mean by that on each step of this pipeline, you need to make a decision. For example, when you create a descriptor, you choose what descriptor to create, and you choose the patch size. So this is one parameter. When you define the transforms, well, you don't have parameters here, so these are open. But when you define the JMM or NMF, you need to define the number of components. When you do the PCA, you define what number of components to keep. So these are the parameters that you want to optimize, and ideally you want to optimize it in the automated fashion, not manually. And we'll get to the point of how it is done using the Bayesian optimization down the line. So let me show you a few examples. So the easiest, or at least theoretically the simplest linear transform is the principal component analysis. So we went through it 2 lectures ago. So all it does, it takes your data and divides it in the component that are orthonormal, and so that they're ranked by the importance. The most important component goes first, second most important goes second, and so on. So in some sense, for those of you who are familiar with the mathematical physics, this is essentially creating the system of orthogonal polynomials. And the beauty of it is that if you start to apply this type of method for any image, you start to get something really interesting, which actually makes you think about the deep relationship between the statistics and physics. So this is an example of the scanning probe microscopy image, which shows some preferential domain pattern. So for simplicity, it is something like a spinodal decomposition. So if I take this image, break it apart in the patches, and then I apply the PCA, then my loading maps, I mean, they show something. So you can see that there is some reverberation patterns, but generally there is regions with a stronger intensity, a weak intensity, and so on. But my eigenvectors, so in this case, the components are images, they start to look like the example of the orbitals from the quantum physics textbook. And there is a very good reason why it is the case. So how do you unwind the logic here? So your first so this system clearly is almost rotationally invariant. So you cannot see any preferential orientation. And at the same time, it has a characteristic size. Well, this is what the spinodal systems are. Correspondingly, if you do the Fourier transform and take the first PCA component, the first PCA component would be essentially a bubble. So it's rotationally invariant and it has a characteristic size. The width of the bubble tells you the disorder. So the second component, by definition of PCA, has to be orthogonal to the first one. So it's end up looking like pi orbital. The second one has to, the third one has to be orthogonal to the first and second component. So it looks like a pi orbital in the opposite direction. Then if you continue, you will see that this principle stands on, and in the end you have a sort of very beautiful depiction of the internal structure of this system. In this particular case, it may be not particularly useful. It sort of illustrates more how the PCA on FFT works rather than tells us something useful about the material, but it's still kind of pleasant thing to see. We can define more useful transforms. So one of the things that we know is that if we have imagine that you have a sample that have several components and you bring it to the X-ray. So you expect that your X-ray is going to be a linear combination of the X-ray spectra for the individual components. And in fact, if you do it quantitatively, you can even do the regression and find out how much the components are present. So we can do the same thing with the sliding Fourier transform. In this case, we can use slightly different methods. So the nFindR, which is very similar to the linear Bayesian unmixing. And in this case, we can try to apply this method on the artificial data set. So in this, as you see, Rama about 10 years ago have generated the artificial crystal lattice, where here you have one periodicity, here you have a different periodicity. And what we do here is that we take a window, as you see, fairly large one, we move it around the sample, and then we run the transform with the two components only. And then we have two end members, and we have two loading maps. And now something really cool have happened. So notice that this Fourier transform and this Fourier transform are exactly the Fourier transform of the pure phase on the left and pure phase on the right. Our abundances change from 0 to 1 and from 1 to 0. So what does it tell us? It tells us that we have so from the point of view of machine learning methods, it of course doesn't know that On the left is phase one, and on the right is phase two. So the machine learning method always starts. So let's put it this way. If your machine learning method produces something that looks understandable and logical for you, this is not something to take for granted. That's actually a major finding most of the time, for the very simple reason that you, when you analyze the image, you know physics and chemistry behind this image. When you analyze the data, human eye is actually pretty good at it. So we can recognize what happened here ourselves. When we use the machine learning method for analysis of this data, it doesn't give us something that is obvious for us because it's not obvious for the algorithm. Algorithm gives us the result, and we use our prior knowledge to make a conclusion whether this result is explainable or not. And in this case, it turns out that result is so good that it is almost obvious. So the algorithm has clearly identified this phase and this phase, and it gives you the right Fourier transform for this one and this one. You can ask me, but how do we know what is the right number of components? So if we use techniques like k-means, like Gaussian mixture model, like BLU, like n-find-r, we need to specify what is the number of the components. So in this case, we said there are two. What will happen if, how do we know the right number? And the answer is very straightforward. When in doubt, just do the same analysis for varying number of components and compare the results. So if you do it in this case, you can see that for two components, we have the perfect division in the phase one and phase two. If we do it for three components, we have the phase one, phase two, and then we see that the boundary between the phases have shown up as the individual phase. And you also can notice that the quality of the phase one started to drop. We start to have some extra contrast here. And then if we tell our algorithm to divide things into the four phases, you can see that phase two is still identified, but phase one now is split into the two complementary phases. So we basically, simply by the examination of the overlap between these images, we can say that this is right, this is acceptable if we are willing to count the interface as the new phase, and this is too much. So it is very easy to come up with a criterion that will basically rule out these phases simply based on the overlap between the regions after some smoothing. So great. Would something like this work for the experimental data? Well, I've shown you in the beginning the example of the molybdenum vanadium oxide with a complex structure. So let's just apply this method for this image and see whether it works or not. And as you can see, this is the image. This is the Fourier transform of the image. It is very beautiful, but it is maybe not very revealing. And this is what happens if we take the image and split it into the, take the sliding window of this size, do the Fourier transform within each window, and then separate it into three components. So lo and behold, one of our components is the empty space over here. You can see that the Fourier transform has only one central peak. So this is a k equals 0, meaning that there is no details here. So this is the second component. As you can see, we have identified this phase. And this is the third component. We identified this phase. And as you can see, the separation is almost perfect. The weight of the phase is 1 here. So this is a pure component. And weight of this phase is almost 1 here. So that's also pure component. So almost, because there is a little bit of leakage in the 0 k equals 0 peak. So basically the conclusion, this method works. Can it work for more complex cases? So let's look at this STM image, where sort of by eye we can say that sometimes there are dimers like this, and sometimes there are structures like this. Can we use the same analysis to analyze the image when we don't have the clearly visible phase boundaries by eye? Turns out that we can. So in this case, we also can divide the image into components. And you can see that there are clearly a spatially ordered region with one phase being dominant and another phase being in the minority. So why does it happen? It happens because in this particular case, we deal with a system which is, has so-called nanoscale electronic phase separation. So physicists, based on the scattering data, speculate that it should have the nanophase regions of the different structure. But of course, the evidence for that is indirect. It comes from the scattering methods. And once we do this transform, we visualize what these regions are. And of course, the nice thing about the Fourier transform is that we can invert it. So inversion of the Fourier transform is obviously a complex problem because of the phase problem. So if it were not the case, there would be no science about the X-ray scattering. But we still can invert the invert the Fourier transform and essentially get a Patterson map, which sort of allows us to visualize these two structures. So we can even get the real space representation of the one phase and the other phase. Now, would other analysis methods help? So a few years ago, we have experimented with the broad collection of the analysis, for example, independent component analysis. This is something that is open for discussion in the future. So our initial comparison was that if we try to compare the, let's say, nFind-R versus ICA, then nFind-R gives us the physically meaningful pictures and the ICA does not. So we came to conclusion that based on the relatively small number of model systems, we came to conclusion that the method has the built-in physical constraint relevant to the system. It works really well. If the method have a different nature, it will still produce something potentially interesting, but much more difficult to interpret. So the principle that can be formulated is that when you choose your analysis workflow, when you build your pipeline to go from image stack to the loading maps, always experiment, always start with the simpler methods first, and always think about what is your physical foundation for the specific unmixing method, because ultimately it determines how well it works and it determines how interpretable are the results. So this being said, sliding transform, especially the sliding transform, we take the image, when we apply the FFT, and then we apply the linear unmixing method, is actually a very powerful method. It instantly gives you some insight in the properties of the object. It is very powerful, it is stable, and it is robust. So what it means is that if you run the sliding FFT PCA on an image, it will always work. Comparatively, things like neural networks very often will require tuning. So they give you more detailed information, but at the price of the need to optimize them and tune them for specific data set. But there is a problem with the sliding FFT. So the problem is that we always need to choose the window size. And here, if we choose the size of our patch to be large, then we have a great Fourier transform. So we don't have the edge effects, but we lose spatial resolution, because the larger is the patch, the more smeared are the features within the patch. At the same time, if we take our patch size to be too small, our FFT is not going to be particularly well behaved, because Fourier transform behaves well when we have multiple objects. If we have a small number of objects, we start to have an edge effect. So it matters where is the patch selected within the image. And if we have a very small number of objects, we can still do the Fourier transform, but it's simply ill-defined. What is very interesting is that if you apply the sliding FFT PCA in this regime, you still are going to get something interesting. But this is something that you need to experiment with to develop a little bit of the intuition of how it works. So the second problem that we have is that the interpretation of the FFT components is actually complicated. So there are multiple ways we can do that. For example, we can take the Fourier transform and fit each peak and then plot the position or the area under the peak. But there are too many components like that. And that brings us to the logic that maybe FFT is great if we want something fast and robust, but maybe we should also look at the image analysis from a different perspective. And the natural descriptor for atomically resolved imaging is the atomic coordinates. So what if we analyze the image by finding all the atoms within the image? And then we try to explore the relative positions and relative arrangements between those atoms. So how can we do that? So this is something that we call the local crystallography. And the easiest way to imagine it is imagine that we found all the atoms within the image. For simplicity, let's assume that all the atoms are of the same type. If so, then for each atom, we can define its nearest chemical neighborhood simply through as the collection of the radius vector from this atom to the neighbors. Let's say first neighbor, second neighbor, third neighbor, and so on. And then basically what we have to do is to analyze the nearest neighborhood of each atom in the image using exactly the same linear analysis. So why is it useful? So originally we thought about this type of analysis in the context of identification of the ferroic variance in the image. So if you have atomic groups, the same atomic group that has a different orientation, you should be able to find it after the application of the finite symmetry group. Practically, it turns out that this is much more useful. So let's just dive into that and see how it works. So this is the example of this local crystallographic analysis of the same image from the same series of the molybdenum vanadium oxides. So this is our original image. So very aesthetically appealing. You can see one phase, you can see a second phase. It is very tempting to say that we have 1, 2, 3, 4 grains of this phase, and then we have some form of the boundaries between them. So maybe it's true, maybe it's not. It's difficult to say. We can get a Fourier transform of this image. Looks beautiful, but again, there is kind of too much information. So let's do a very simple operation. Let's find all the atoms in this image. In this case, it's easy. We just can use the something like log blob transform from the scikit image. Then we find the neighbors of the images, and then we choose the characterize each atom by the vector of distances to the 6 nearest neighbors. So each atom now has 6 parameters, distance for the 6 closest neighbors. Then we are going to do the k-mean clustering on this vector. And then we are going to color each atom by the cluster label. So this is type 1 atom, this is type 2, type 3, and type 4. And lo and behold, you can see that we instantly separated our image based on the local structure around each atom. So we identified one phase, we identified the atoms with a certain neighborhood inside the second phase, and so on and so forth. So we can split this image further. So as you can see here, there are 4 clusters, and you can visualize the spatial localization of the atoms in each 4 clusters. So this is and since Fourier transform is a great way to highlight what goes on, we can create this, separate the atoms based on the chemical neighborhood, and we can calculate the Fourier transform. So you see that these are atoms which are sitting almost on the ideal hexagonal lattice. These atoms, they clearly have some structure, so there are some peaks and some ordering here. These atoms seems to belong to some form of the amorphous phase. At least it is considerably more spatially delocalized. It seems to be sitting on the, roughly speaking, the boundaries between these phases. I mean, of course, it has to be quantified, but simply based on the visual examination, it looks to be that these atoms are amorphous. And this atom seems to be complementary to this one. So if I were analyzing this, I would probably pull these two into the one group. As I said, you always choose the number of group based on your external guidance. You rarely have the identification based on the data only. And now the interesting part. So for the phase that, for the system that clearly has two different phases, we learn how to separate the phase. But what if the system looks absolutely uniform to an eye? So let's take another region of the same material and run exactly the same type of analysis. So we can play with our descriptors. So we can analyze things based on the radius vector. We can characterize each atom based on the angles that the radius vector format. So there is a considerable flexibility in how you want to represent the data. But look what happens. So once we've done it, you can clearly see that there is a antiphase defect inside the system. So you see that this part is absolutely uniform. This part is absolutely uniform, but there is a line along which the atoms shift by the half of the period. And you can see it even better here when you can follow the green to red column. And then you see that here, these columns are shifted by the half of the period. So, I mean, perhaps it is possible to deduce this behavior by looking at this image only, but we realized that it happened only based on this analysis. So if your image has a lot of small details and the change in the structure is relatively small, machine learning methods work like a charm. They will simply visualize any irregularity inside the structure and make it visible loud and clear. Then you can ask a question. Look, in this analysis, you took the atoms, you took the coordinates of the atoms around the central atom, and then you apply the k-means clustering. So k-means clustering, by definition, tries to split things in the group. That's what clustering means. And you were able to identify different atoms inside the system, and that gives us some idea about the chemistry of the system. But what if instead of k-means clustering, you use a principal component analysis? So principal component analysis tries to do a very different thing. It tries to determine the degrees of variability, continuous degrees of variability inside the system. So what happens if we apply this approach in this case? And it turns out that it also works. And think about it this way. So if we take an atom and define the nearest neighborhood around it, this can be represented as a feature. And this is a feature formed by 6 vectors. So each vector is basically the radius vector from central atom to one of the 6 neighbors. If we apply principal component analysis to this feature, we split it in the components, but the important thing about the PCA is that each component in the PCA have the same meaning as the original spectral data, which basically means that the PCA component in this case would also have the meaning of the vector. But these would be the vectors of distortion of the surrounding atoms compared to the central one. And you can visualize them as the way it is done here, when for each atom you draw this distortion vector. And lo and behold, you start to see that there is some beautiful internal structure here. So for example, the first PCA component is essentially a constant. It's basically the average of the data. So nothing to see here. It just shows some variability because of the different type of atoms inside the system. However, the second component shows that this is essentially the polar displacement of the central atom compared to its neighborhood. You see that this polar displacement follow the positive negative pattern, so these dipoles cancel out, but you can visualize them. You also can see, and that's sort of important, that you will not see this antiphase boundary visible in the polar displacement, which means that in this case, the antiphase boundary does not induce ferroelectricity inside the system. So it doesn't affect the polar ordering. Then the third component shows a more complex deformation. You can see that these 4 atoms shift in one direction, these 2 shift in the opposite direction. So it's a little bit more complex mode. And you see how it can be distributed in the real space. And this mode, whatever it is, shows that is the one that shows this antiphase boundary. And if you keep looking, you see that these actually have the physical sense. So what this most resemble is the normal modes in the molecular vibration, but the normal modes in the molecular vibrations appear based on the group theory analysis. So they are supposed to be orthogonal and represent and be sort of connected to the representation of the group. In this case, this is a statistical normal mode. So it is not, it would be orthogonal because of the properties of the PCA. However, it's not connected to any group theory. It's connected to the representation of the data. And interestingly, it has a physical sense. Now, can we do it for the same analysis for the image that I've shown you in the very beginning? And then I said that this is a ferroelectric domains, but you cannot see it. Answer, yes. And lo and behold, we start to see something truly interesting. So this is our image. We can define our building blocks. And as I said, the size of the window is a hyperparameter. It is always a good idea to experiment with it. So we take our images, we find all the atoms, we create the descriptors like this one, and then we run the PCA analysis and we plot the eigenvectors and the loading maps. And lo and behold, our first eigenvector basically shows that the central atom is in plane, nothing happens here, and then the atoms around it shift in one direction. So in this case, we analyze not the neighborhood, we analyze the image patches. So the atoms around it shift in the one direction. So what does it mean? It means that this is a polar displacement. It's a polar displacement in this direction. And you can see that now this image start to look like this, which basically means that we have visualized the ferroelectric domain where this displacement is positive, and we have visualized the ferroelectric domain where this displacement is negative. Now, the second component is the displacement in the orthogonal direction. Again, see that we have a domain where this displacement is negative and the domain where this displacement is positive. You can also see that the domains in this image and this image are complementary. And that makes perfect sense because the polarization vector in this material can have 4 possible orientation in the image plane. So basically, this shows us this component in the 1, 1 direction, and this shows us the different component in the 1, -1 direction. And this component are independent. And then the interesting thing happens if we start to look at the elder components. So for example, if we look at this component, you can see that it tells us something different. So in this case, there is no polar displacement, but you start to see the oxygen atoms. So it's change of the intensity of the oxygen. And it's also the relative change of the intensity of the A cations. So first we thought that this is a noise because we thought that there are only these outliers here. But it turns out that if you look more carefully, you can see that there are domain walls are actually darker. So there is some physical mechanism here that we don't quite understand, but PCA reveals it. And then speaking about the artifacts. So look at this component and this loading map. So if you look here, this component looks almost like the component number 1. It is essentially the displacement in the 1, 1 direction. But the spatial map looks totally disordered. So how do we interpret it? So, well, machine learning is not ideal. So in this case, the difference is that look at the edges of these atoms. So this is negative, negative, positive, positive, and this is positive, negative, positive, negative. So this component appeared because our choice of the feature is not ideal, and somehow it locked onto these edge effects. However, we can also figure out how important is this component. And you can see that basically this is already in the noise. So you can represent the PCA as the explainable variance. So you can see that our second and third components, these ones, are important. And this component is already, it's not exactly noise, it has some sense, but it's relatively less important. So if we wanted to improve this analysis somehow, for one of the things we could do is we could create a more complex descriptor, for example, that follows the shape of the sort of four-angle star or something like this, which will exclude this type of effects. But the more complex the descriptor, the less universal it is. So at that time, we haven't done that. So can we use it for more complex systems? So if it works for ferroelectrics, where we know what the order parameter is, can we apply it for a more complex system where we don't know what the order parameter is? And the answer is yes, we can. So this is the example of the solid solution between molybdenum sulfide and rhenium sulfide. So if there is a very little amount of rhenium, you can see that it forms the bright atoms here. So rhenium is much heavier, so you can see it. If we start to add more rhenium in the system, you can see that, first of all, you have more bright atoms. And secondly, even by eye, you can see that the symmetry of the system changes. So this one is has a sort of normal hexagonal symmetry. This one forms this, is monoclinic. You see this coexistence of two sets of the tilted lines. And you can see it remarkably well in the Fourier transform or in the pair distribution function analysis. So if we look at the pair distribution function, you can see that there is only one type of neighbors here. So there is a narrow single peak. Then peaks start to be more disordered. So they broaden and they start to split. If we keep increasing the amount of rhenium, the splitting increases. So here it's split in one direction. Now you can see the splitting in the four components. And here the splitting is complete. So in the physical language, this is called the symmetry lowering transition. And this is one of the things that physicists are really interested about, because a lot of physics is related to the symmetry lowering upon the phase transition induced by doping or by temperature and so on and so forth. So however, we of course can analyze it from the point of view of Fourier transform, but it's also interesting to analyze it locally, right? And it turns out that we can actually do that using the same principle of the local crystallographic analysis. So we take our image, we find all the atoms inside this image, we do the same type of PCA analysis. Now we have the beautiful representation of the distortion modes. And then we can do a next neat trick, because in our bismuth ferrite, all the atoms were the same. So all the bismuth atoms are the same, all the iron atoms are the same. We cannot distinguish them. In this case, we know that there are two types of atoms. We have the rhenium atoms and we have the molybdenum atoms. And we know that for each global composition, we have a variability of the local composition. So if we have a small concentration of rhenium, we have either the zero rhenium atoms or one and very rarely two rhenium atoms inside the cluster. But if we have, let's say, 55% of rhenium, we have a broad distribution of the rhenium atoms around the chosen central atom. So in other words, when we study the system by electron microscopy, we can study it one atom at a time, which means that we can study the symmetry breaking on the level of the single compositional fluctuation. So one global composition has multiple local compositions. For scattering methods, they average out, but for electron microscopy, they can be observed in real space. And it turns out that in this case, we can actually analyze how the symmetry breaking happens simply by plotting this magnitude of this distortion mode as the function of the local neighborhood atoms. And you can see that virtually for all our materials, if we have 0 or 1 atom, we don't have a splitting. And then if we have 2 or more, then we start to split our local neighborhood, which basically means that if you apply electron microscopy combined with relatively simple image analysis, you can actually start to study the symmetry breaking on the level of single atom. So compare it to the Electron microscopy, compare it to scattering, where the amount of material has to be actually quite significant. So smallest you can do is things like focused X-ray, but you still need several tens of nanometer volume of material to produce a measurable signal. So why is it useful? If you apply this approach for a single material, it's great. You can compare the result to the X-ray scattering. But imagine if you apply this approach for something like a flake of the 2D material, which has been grown with the gradient of concentration. So a single flake, in this case, will contain multiple chemical composition. And then basically you can study the chemistry and physics of the phase transition just by 1 nanometer volume of material. So what about chemical dynamics? So we're getting to the end of the lecture. Let's quickly look whether the same approaches work for chemistry. So in this case, our data typically looks like this. And analysis of this data is a little bit more complicated. So for dynamic data, where we have to be cognizant of the dose, because the larger is the dose, the better we see atoms, but there is also the higher damage to the material. This is the case where we typically use the deep learning to find the atomic position. So the simple blob log type methods don't really work very well. But we will illustrate how it works in a few lectures from now. But for the time being, let's assume that we have found all the atomic positions. And then we can apply the similar local crystallographic approaches. And then lo and behold, we start to see very interesting things. So now if we analyze the neighborhoods of the silicon atoms, so we found all the silicon atoms, we build our descriptors as the patches centered on the silicon atoms. Then we have run the Gaussian mixture model analysis of this data. Look how our components look like. So these are almost textbook examples of the structures that the silicon at the edge of the carbon can form. So here you can see the armchair edge with the silicon termination. This is the same edge, but with the different orientation. So they're rotated by 60 degrees. So this is the silicon sitting on the zigzag edge. And then if you go through these components, you can basically see that all of them has physical meaning. So this one is particularly beautiful. You see these are 3 carbons and these are 2 silicons. Now, as I mentioned before, these are the statistical components. The fact that they look like a human identifiable object happens because that these are the structures that are present in our data. And what our analysis did is to discover them in the unsupervised fashion. The limitation of this analysis using the linear model is that we find the same object multiple times depending on rotation. So this one and this one are the same because the same physically, they differ only by the rotation in the image plane. So this one is the same, by the way, this one is the same. So this is the limitation of the image method. They create too many classes. Sometimes you can manually combine them. Practically, the better solution is to use the rotationally invariant autoencoders because they already allow to do that without the manual assembly. But does mean that it cannot be done by the methods. Final thing that I want to illustrate is what about the mesoscopic data? So what if we don't have the atomic structures? Would this work? Interestingly enough, it will. So this is the example of the data where we observe the thermally induced phase transition inside the barium titanate. So basically what you see is the domain pattern, which is just the dark lines on the image. So you can see that at one temperature, they're all oriented in one direction. On increasing the temperature, the domains change orientation and progressively start to be oriented in the different direction. At high temperature, they disappear. It's a phase transition. Then when you lower the temperature, first they form orientation in this direction, and then they kind of go back to roughly where they were before. So it turns out that we can use exactly the same type of pipeline in order to analyze this type of images. Start with the video, create sub-images, create sub-transform. So a small trick here is that if you have a video, typically the number of the image patches that you get is way too large. It will not fit in the memory. So what you can do is you can train your transform using the subset of these patches. And then once the transform is trained, you apply it for the full images. And then you visualize the statistics or images. And this is how the results will look like. So I put the notebook for that. So we'll see how it happens in real time. So this is the typical GMM components. We can analyze their dynamic as the function of time. So you can see that if we choose a component for the analysis, you can see that once we change our temperature, some of them disappear, some of them actually become stronger, and you can clearly see the dynamics of the phase transition by eye on this diagram. And in fact, you can see both transitions from this orientation to this orientation, because this component clearly has a second transition over here. So we have first transition, we have the second transition, we have high temperature phase, then we have transition back into the second phase, and then into the original phase. So this is all follows from this histogram. If we want to make it a little bit more quantitative, we can just analyze our favorite NMF or PCA method and kind of just look at the dynamic. Final thing that I want to briefly illustrate is the use of the Radon transform. So this is the transform that allows us to find the oriented features. That's the nature of the Radon transform. And as the result, if we have our data and we apply it, it basically allows us to highlight where the interesting structures are. Okay, the final thing that I want to briefly mention is whether we can apply this type of transformation for more complex data sets. And one of the things that people are very excited now in the electron microscopy is the 4D stem. So this is, Gerd is going to talk more about it. Basically, this is the technique where we focus our beam to the subatomic diameter, and then we get the Fourier transform, and then we get the diffraction. So it's a very unusual diffraction because in this case, the width of the peaks is much larger than the spacing of the peaks. So our data looks like overlapping disks. Turns out that linear unmixing is a really great way to get initial idea about the structure of the PCA dataset. So this is the example of how the some of the first 4D stem datasets we got look like. So this is about year 2015. So dataset is beautiful, but there is a lot of data. In fact, you kind of feel like you are drowning in data. And if you average all of them, you get a normal dark field image. But in this case, you lost all this information present in each PCA component. Sorry, in each Rankine-graph. So if you apply the analysis such as PCA or NMF, you start to see the beautiful clustering. And now you can visualize that there are two different phases here simply based on how the colors appear. So let's call it a lecture. So do you have any questions that I can answer before we go into the collabs? Okay, so let's jump into the collab directly. So the collabs for this lecture are on the GitHub as before. So you're welcome to go to the repository and run it. So there are two collabs. One illustrates the dimensionality reduction for the image data. Another is for the videos. Basically, let's start from the image one. So as usual, we start with the installation. So in this case, we are going to use the Atom AI package developed by Maxim Zyadinov. So the reason why we are going to use it is because it implements the well-tested function for the splitting the image into the patches. So we don't have to deal with the patch overlapping the border and so on and so forth. We are going to import some of the usual libraries like matplotlib, numpy, and a little bit of the functions from the scikit-learn. So let's start with the image like this. So this is just the image of the two-phase material. So these objects are the nickel oxide, which has a rock salt structure. This is the lantern strontium manganite, which is the perovskite. So if you look at this image carefully, you can see that there is bright atoms and dark atoms. So these are A site and B site cations. So you are not going to see the oxygen unless you look really carefully, but sort of let's start somewhere. So now let me show you the few type of analysis. One of them I pre-run in the notebook because it takes quite a while, and then few of them we are going to run manually. So let's start with the preparation of the image stack. So this is something that we had to do over and over again. So what we do is we define the window size. So this is the size of our sub-image. We define the step size. So what is the sampling grid? Generally, depending on what analysis you want to do, 64 is large, but I'll show you why it is important. And then we are going to use the Atom AI in order to create the coordinates. So coordinates will simply be the, let's run it. So coordinates will simply be the array of the coordinates of the image. And then we are going to create the three objects, the image stack, the coordinate grid, and frame grid. So the image stack, it is just the number of the patches. So as you see, even a relatively small image creates something like 15,000 patches if we divide it using these parameters. So each patch has a size 64 by 64. And this is our frame. So Atom AI is developed to apply equally for images and videos, which basically means that we always have a frame, except that in this case, our frame is always going to be 0. So if we look at the com grid, it is basically the coordinate of the centers from which the patch has been taken. And you can see that the number of the objects in the com grid is the same as the number of the image patches. Obviously, the dimensional, there are two elements here, X and Y. The frame grid is basically just the array of the same length, but each element here is 0 because everything came from the frame number 0. So this is the function that applies the Fourier transform. So in this case, so remember I told you that we can now use ChatGPT to do a lot of things for us. So important thing is to, in this case, I actually tried to do that. One has to be careful because it requires several iterations for the ChatGPT to do exactly what I wanted. So it did the incorrect Fourier shift in the beginning. So you need to know what you want to accomplish before you can get it out of it. So anyway, then I define the function that creates the Fourier transform. I take my images and I apply the Fourier transform to them. So if I check the shape of the object, it is the same shape. So Fourier transform doesn't change the image size. Then I can visualize this object. So this you can see only the central peak. So let's play with the scale a little bit. For example, let's see if it works. Yep, much better. So now you can see that each object is essentially a Fourier transform. So you can see peaks, and then if I run the Gaussian mixture model, this is what I get. So this analysis takes about 10-15 minutes, so it's too long to run it in real time, but therefore I pre-run it. And this is what you will see. So this would be the Fourier transforms of the components. And this is how the special maps are going to look like. So why is it important? It is important because I started with the image. And of course, in this case, I can analyze it by eye. But it is very easy to imagine the situation when the image is simply too large. For example, this is a 2024 by 2024 image. I can easily take an image which would be 32,000 by 32,000. That would be a little bit more difficult. So I take this image, I apply a very robust operation of splitting it into the stack of the image patches. I apply a very robust operation of Fourier transform. I apply a very robust operation of Gaussian mixture model separation. And now, lo and behold, the image is separated into the 4 components. So what can you notice here? You can immediately notice that the blue phase, which is JMM number 1, which kind of has very nice Fourier transform, this is clearly our rock salt phase. No surprise here, this is just nickel oxide. You can notice that we always have a phase, which is in our case number 3, which always appears between the rock salt and perovskite. So it's almost like a transition phase, and we don't know whether this is a real phase or this is the smearing effect of our chosen descriptor. So we cannot answer this question because this is the reason why I have shown you the simulated data, because even in the simulated data, when the interface is abrupt, this analysis will always introduce smearing. So if it shows that there is something unusual here, it serves as the pay attention and explore this in more detail. It's not an answer. Notice that this small region over here shows only as the phase number 3. So it's either our window is too large, sorry, or this is the same interfacial phase. And now what is very interesting is that you can see that the perovskite region is split between the 2 phases, so phase number 2 and phase number 0. And these phases have almost the same Fourier transform, but clearly the analysis have split them for whatever reason. The question is, why did it happen? And the answer is very simple, because machine learning analysis is a very powerful tool, but it's also a very blunt tool. If we tell our algorithm that we want to split our image in exactly 4 phases, it will do it no matter what. It will lock on the arbitrary small difference within the data. And basically, it split it for us in 4 phases. Now you can ask a second question is, why is the perovskite in this part of the image looks to be different than the perovskite in this part of the image? And to the best of our knowledge, meaning spending multiple years analyzing this type of data, this is exactly the effect of the microscope scanning system non-idealities. So the reason why GERD lectures were in the beginning of this course is because machine learning will find everything. It will find the true phase variability in the data, and it will find the variability associated with the way the microscope works. And this type of behavior sorry, this type of behavior is in most cases associated with the non-ideality of the microscope performance. Now let's do something fun. So let's start with the much smaller image size, so the analysis is faster. So let's make it 32. Let's run the same codes. So let's do the Fourier transform. So again, we have chosen the Fourier transform data. So now if we run FFT, our window size is smaller, so the features actually look larger. Let's see how the Gaussian mixture model is going to work in this case. So last time I ran it, it was closer to a few minutes, but let's see if it happens, if it runs fast enough. So while it is running, let's run ahead a little bit and also look how we can apply the principal component analysis for this method. So this code basically instantiates the PCA from the standard scikit-learn. So this is our scree plot, which tells us kind of the fraction of the information as a function of the component number. So you can see that most of the data is sitting in the first several components. And this is how the PCA components are going to look like. So these are the components, and sorry, this is actually a typo. These are the loading. This should be the loading maps, and this should be the components. So you can see that there is a something interesting on the first component and second component. So the first component separated the phases. Second component and fourth component showed this unusual phase, so it's something fishy going on. But the third component start to visualize this type of straight lines. So these lines are actually the artifacts associated with the microscope work. This is simply the jitter noise from one line to another line. So PCA is exceptionally sensitive and visualizes this really well. So the high order components, they start to be the non-idealities of the Fourier transform. So now let's go back to our Gaussian mixture model. So if our window is smaller, you can see that our phases did not identify that well. So we can still see the difference between the nickel oxide and the perovskite. But now we start to divide the perovskites, and this type of structures is essentially the Moire effect. So what happens in this case is that our lattice have some periodicity, our sampling grid have periodicity. These periodicities are not the same. So if you superimpose two periodic structures on top of each other, then you start to have this type of beating effect when you have a larger range periodicity appearing in the system. So let's experiment more with this, and rather than analyzing the Fourier transform data, let's just analyze the original image components. So now our image, okay, I need to remove this one, of course. Give me a second. So now our sub-images look like this. So some of them clearly have came from the nickel oxide. Some of them has clearly come from the perovskite. So let's repeat the Gaussian mixture model analysis and see what happens in this case. So now as the small kind of, oops, remove this one as well. Now as the small exercise, so try to think about how we should choose the window size if we do the Fourier transform versus the analysis of the real space feature, and sort of drop it in the chat. So for example, if we do the sliding window and FFT, should we choose a big window or small window? If we run the sliding window based on the identity transform, just take sub-images, should we take a big window or small window? So look what happened in this case. So now one of our components is essentially the perovskite lattice. but that clearly didn't work very well because you start to see this beating pattern. So, and you see that the components show essentially as the straight lines. So in this case, the unmixing didn't work particularly well. So again, based on the some experimentation, it is possible to find the parameters where the analysis produces the clear phase map. So as I mentioned, the hyperparameter in this case is window size. So if we choose the window size being 48, then things will work differently. So if you meditated about it, then the answer is you generally want to choose the size of your subimage to be such that it is in some sense commensurate with the lattice parameter of your system. So you can choose it to be one lattice parameter, two lattice parameter, 1.4, which corresponds to the atoms in the nearest neighbors in the 1,1 direction, so square root 2. So you basically do it based on the expected physics of the system. The problem with the linear analysis, as I mentioned, is that it doesn't treat the rotational variance very well. So if you have the same object present in the multiple rotational variants within the image, basically it doesn't work at all. If you simply have the image which is rotated, like is the case now, it works, but not nearly as good as it would be the case for the normally oriented image. So again, it worked, but you clearly see the beating pattern inside your images, and you can even visualize it within the principal component analysis as well. So this is not good. So here things didn't work out. So there are a few other things we can experiment with, like try to see how well our classification worked. So in this particular case, not really well. But if you look at this analysis for the large window in the Fourier transform, so let's see if let's just do it. And then we'll return back to it after the next step. So let's analyze the Fourier transform data set for this window size. This one. And while it is working, let's look at the second type of analysis, where we analyze the data using the patches which are centered on the atomic units. So in the first part of the notebook, we choose our sampling grid based on the just usual sliding window. So now we actually are going to find atoms. So how is this notebook organized? So again, we start with the installation of the Atom AI. We have our libraries. And in this particular case, we are going to download the results of the analysis done using the deep convolutional networks. So the only thing that we care about is that someone have already analyzed the data, and they give us the raw data, they give us the output of the deep convolutional network, and they give us the coordinates of the atoms that we extracted from the output of the deep convolutional network. And as I mentioned, we are going to explore how it can be done in a few lectures from now. So this is how the image will look like. So in this case, this is our figure, and you can see that this is a bilayer formed by the ferroelectric material and the non-ferroelectric layers in between. And in fact, in this case, if you look at the image carefully, you can see that there is some form of the distortion running between the image. So I'm not sure if you would be able to see it on your computer screens, but you can clearly, but there is something here. So this is what the analysis using the deep convolutional network does. Basically, it takes the image like this and finds all the atoms inside the image and finds and classifies. So you see that there is a red atoms corresponding to the first sublattice, the green atoms are corresponding to the second sublattice, so you can have an image, the compound image of the lattices and the model prediction for sublattice 1 and sublattice 2. And then we are going to do exactly the same analysis as we did in the first case. So we now are going to define our window size, but in this case, we are going to extract our patches using our coordinates. So our patches now are centered on each atom inside the structure rather than on some abstract sampling grid. And if we visualize these patches, you're going to see that they are sort of much nicer behaved. So it's kind of unsurprising because we have chosen the low intensity cation as the center of each atom. So now if we run the k-means clustering for this structure, we are going to get something like this. So this is our cluster centers. You can see that they are nicely representing different type of atomic structures inside the material. We can run the Gaussian mixture model, same type of approach, and then we can visualize the labels of the k-means clustering and the Gaussian mixture models. And now you can see that we now separated our data set into the visible structure. So we visualize the k-means allowed us to separate different type of atoms and layers, and it provided us some information about the ferroelectric domains. So the GMM did a much better job about it. So now you can see that we start to visualize the domain structures associated with this small contract over here. So overall, we start to get the idea about what is the structure of the ferroelectric domains inside this material. So while the process is going on, let's go back to our original analysis where we try to analyze the GMM on the Fourier transform image for intermediate size and look at the results. So again, we reproduced our original behavior. So we can compare the PCA results and the Gaussian mixture model classes. So it gives us a little bit of idea of what is the relationship between these images and what is the relationship of these images. And that's basically how you can analyze the structure of the, that's how you can analyze the structure of the images using the Slidign transform. So let's make a pause here and do you have any questions? So what do we have anything in the chat? Okay, Manya have already answered to this one. Okay, so if there are no questions, let's go to the second example, meaning the notebook for the analysis of the video data. So let me go back to the beginning here and share the screen with, share this screen. So this is the notebook 7.1. So this notebook illustrates the application of the dimensionality reduction for the video data. So again, we use exactly the same collection of the libraries. We use Atom AI as a parser for our image in order required to build the image stack. We use the same basic libraries, so matplotlib, readspec, numpy, and scikit-learn libraries. So we install all of these libraries. So Atom AI, we download our data objects. So then we import the additional analysis modules. And then let's look at what our data looks like. So once we upload the document, we will have the data. Oops. This one. We will have the data sitting in our cloud space. So this is basically a large collection of the image files. And if we open them, of course, it doesn't want to open TIFs. It takes a while to open TIF. Okay, so this doesn't seem to visualize it. But anyway, this would be a large collection of the image files, and it would be the temperature profile. So the first thing we can do is to examine the data. So now that they're imported in the single array, we can just take any image inside this array and visualize it. So this is how they look like. So this looks exactly like the data set that I have shown you, for a good reason, because that's what we use for the illustration. We of course can choose any choose to visualize any other data set, for example, for a different temperature. So in this case, we have plotted the image at the different different temperature. So then we can create the image stack. So in this case, we define our random seed so that the analysis is reproducible. We define the number of the sub-images. So remember, if we have a video file, we almost never can create the patches from the whole image stack. Even from one image, we typically have a very large number of images that can overload our memory. If we have a video, if we start dividing it into the stacks, into the patches, we can very quickly run out of memory. So what we are going to do is we are going to make a trick when we select a number of sub-images for each image. We use the utility which is called extract random sub-images. So basically from each image, we select 500 random sub-images. And then once we create them, we are going to train our transform using these sub-images. So this is how it looks like. So we run in this case, we run the GMM model. And the question becomes, what are the physical meaning here? So what is the physical meaning of the GMM components? So very simple. This component means that we don't have any domains. This component means essentially that we have an edge, as is this one and this one, just the edges at different position. And this component means is that they try to approximate the stripy domain pattern as close to it as possible. It's not ideal, but that's what it is. So then we take this data set and put it in the pandas data frame. So that's a kind of convenient way to keep track of temperature, frame, and the number of the GMM component. And then in order to visualize it, we are going to use a trick called the kernel density estimate. So basically, the only reason we are using it is to represent our data in the way which is slightly more pleasant to the eye. So we just create a kernel density estimate, but we could easily use a histogram. And then we visualize the behavior of these components as a function of the frame number. So each component is corresponding to either this component, and so on. So there are 8 of them overall. And here you can see how their intensity depends on the number of frame. So this component seems to be more or less constant, and then when it becomes much more pronounced, and then it again goes down. So remember that this component corresponded to lack of the contrast. So that means that essentially empty spots on the image. This component is number 2, is very strong in the beginning and in the end. Then it goes down. It's almost completely absent in this region. Then it reappears and then it becomes strong. And the same thing as I observed to the component number 6. So let's look at the component 2 and 6. So obviously numbering in Python starts with 0. So these are the components that correspond to the simple edges. And then all the other components, the component 3, 4, and 7, they don't show up at lower temperature. Then they appear in this temperature interval. Then they disappear. Then they reappear in this temperature interval. And then they disappear again. So basically, just examining this diagram, we can make a conclusion about which components, how this component intensity changes with temperature. And that tells us what are the phase transition temperatures. The caveat in this case is that these components are clearly correlated with each other. So it doesn't make any sense to discuss component 1, 2, 3, 4, 5, 6, 7, 8 separately. We really want to find which of these components change together. And that's exactly what we can accomplish using the non-negative matrix factorization. So in this case, we take all our data set, and rather than interpreting it as 8 components, we represent it as 2 NMF components. So, and then we see how the weights of these components depend on the function of temperature. So, and then we can also visualize what these components are. So in this particular case, one of them is dominated by 1 and 5, another is dominated by the remaining components of the system. So we can run the same type of analysis using the Fourier transform applied to the image patches. So in this case, you can see that the behavior is slightly different, but again, you can see very clear phase transitions here and here. And you can use the same trick for the analysis of the behavior of the NMF components on the increasing and the decreasing the temperature. So to illustrate what we are seeing here is that all we have to do is to see the behavior of the data. So one important thing is that the color here is the temperature. So as you can see, we see a somewhat clear hysteresis between the 2 components, saying that one of the transitions, so actually both of the transitions have temperature hysteresis. So we start to see that forward and reverse curves are shifted with respect to each other. And again, we can explore the components and figure out what it means. So, okay. So let's stop it here. And do you have any questions? Okay, so other questions in the... Okay. Okay, so just to recap our discussion. So very often, once we have the image or video data, we need to start to explore what is there. The starting point for this exploration is almost always the global analysis using Fourier transform type of analytics. So it's a great start. Very often it is not sufficient. If the system have the significant distortion, or if there are multiple phase regions of the phases are sort of intermixed with each other, then the global Fourier transform can give you a hint of what these phases are, but maybe not separate it very well. So the only way to do that is to use the Fourier filtering of the data. So the way to get around it is the sliding window transforms, which basically has several components. The component number one is the selection of the descriptors. There are multiple ways we can do that using the uniform sampling grid, using the atom-centered sampling grid, using the time delay sampling grid, and so on. So the step number, our descriptor can also be based on the atomic coordinates only. Then we throw away all the other data in the image. The second component is the analysis pipeline. So analysis pipeline means that we have these image patches or atomic objects. We apply some form of transform, either identity, meaning we don't do anything. We can use the Fourier transform, which highlights the periodicity. We can use the Radon transform, which highlights the presence of the linear features. So whatever transform is most congruent with the type of behavior that you want to analyze. Then on top of this transform, we apply the dimensionality reduction method, which can be PCA, NMF, Gaussian mixture model, Bayesian linear unmixing, and so on. We can also apply the more complex transforms, such as variational autoencoders. So we'll get to this point later. And once we do that, we look at two things. We look at the statistics of the descriptors and how they're distributed in the image plane. So these are our loading maps. And we look at what the components are. So that tells us what is the physical meaning of these loading maps. We can use it for images. We can also use it for video data sets. There are some tricks that we need to play in order to deal with the large volumes of data. Thankfully, we can train the transform of the subset of the data, and we can apply it for the full data set. So that's the way to have it done. So these transformation pipelines have the hyperparameters. The results of our analysis depend on these hyperparameters very much. We need to tune them. If that pipeline has one or two steps, like select the window and select the number of k-means or the GMM components, we can do it manually. If it is more complex than that, then we need to do it automatically. In order to do it automatically, we need to find a way to close the feedback loop, which basically means that we need to identify what is our measure of quality of the outcome. For example, do we want to segment the phases, and then we can have the quality of the separation as our measure of performance, or is it something else? So this is something that we didn't discuss, but for the time being, but this is something that we will explore in the context of the Bayesian optimization for the analysis. So if there are no more questions, then let's call it a day. As a reminder, feel free to send the emails to me and my colleague if you have any specific problems that you want to discuss, and either as a part of the summer school, or if you want to discuss them kind of one by one. Thank you, and bye.